Assalamu alaikum everyone, and our today's topic is electric potential. Right, so to understand this, let's suppose just some space. Right, I have taken this space, this part of the page, and I call it just a space. There is nothing over there. Dot I have made are just so that they can show you that this is just some empty space. Okay, these dots are nothing but the you can say the coordinates of empty space. All right, so the electric potential is a number. It's a number which depends upon the intensity of electric field, right, and the work required to bring a charge to a certain point in an electric field, right? So that's why we say that electric potential is a number. It's just an abstract number. All right, it has nothing to do with the kind of actual realistic thing. You cannot actually hold an electric potential, so it's just a number. And let's suppose now here in this point the potential is 0, and at this point the potential is 0, and at all the points the potential is 0. Why? Because there is no electric field in this area, right? So if there is no electric field, so there is no electric potential at all these points. The electric potential V equals to 0. Here also V equals to 0, and also V equals to 0 here. So at all the points the electric field is, the electric potential is equals to 0. But what happens if I just want this electric potential to have a value, a non-zero value? Then I have to just introduce a charge over this space, or in other words we can say that I want an electric field in this area. Let's suppose now I have a charge plus positive charge. Right, now what happens is that now this V won't be equals to 0, this V won't be equal to 0, and this V won't be equal to 0, because now there lies a field around these points. All right, remember that these are just empty space points. These are not charges, these are just empty space points. So when I introduce a charge in a free space, what happens is that the points around this charge will have some value for the electric potential. Now how would we calculate that electric potential? Coming to the point, electric potential is its unit is joule per coulomb, right? The units of electric potential is joule per coulomb. Now if we take just this point and we say that the electric potential is any non-zero value over here. Okay, so let's say if electric potential is 30 joule per coulomb, let's say. Okay, so what does it mean? What data or what information this electric potential gives us? It means that this, at this point, 30 joules of work should be done on a unit charge to bring it at this point, right? Or 30 joule is the required energy of a particle, of a charge, to stay at this point, right? So for the condition for a charge to be at this point is that it should have 30 joules, right, so that it could actually stay or even pass through this point, right? So from here we can conclude that electric potential is the energy required for a charge to stay at this point, or electric potential is the work to be done on a unit charge to bring that charge from any other point in the space to this point. Okay, so now coming to the point. Here, this 30 joule is the work. It is the amount of energy, and this energy is called the electric potential energy, right? So electric potential and electric potential energy are related to one another. Okay, so 30 joules here is the electric potential energy, the energy required for the charge to or the charge to have this energy just to stay at this point, right? Otherwise the charge cannot reside on this point. Okay, so coming to our definition, the amount of work needed to move a unit of charge from one point to another inside the electric field is called the electric potential. Okay, the amount of work needed to move a charge from one point to another. Like, let's say the point A is at infinity. Okay, what is the infinity point? It means that it is very far away from this charge, so that it won't actually experience any field. So a point which is actually very far away from this area. Okay, when we want to bring a charge from that point to this point, we have to do work of 30 joules for that charge, and this ratio is called the electric potential. That's why we call this as an abstract number. It is not actually a real value, it's just a number when multiplied by the charge gives us energy. Okay, so that's why electric potential is important. So right, so this is here if we have defined electric potential energy. So first we are going to read out the definition. Here I've written the equation of electric potential is V equals to U by Q. You've already seen it here. Okay, V equals to U by Q equals to, U can be replaced by W divided by Q. Okay, because this potential energy, this electric potential energy is the work which must be done on a charge to bring it to this point. That's why we have replaced U with W. These are interchangeable. So this is the equation for our electric potential. And the total potential energy a unit charge will possess if located at any point in an electric field, this is called the electric potential energy. Okay, it is usually denoted by U. This is the electric potential energy equals to QV. Okay, here's the fun thing. Now, knowing the charge Q, right, and knowing a number, the electric potential is a number, is an abstract number. Knowing the charge Q and this number, we can calculate the energy required to move this charge over to this point. So this energy is actually the multiple of charge Q and V. The charge, the amount of charge, and the value of V at this point. Okay, so value of V actually depends upon the orientation of whether this point is closer to this charge or whether it's very far away from this charge. So every point in this field has its own V value, electric potential value. So when we multiply that value, that specific value of a point, with our charge, we get the energy required. That's why this electric potential is important. Otherwise, why would we need it? Why would we need an electric potential? Because this is just a number, we don't actually need it, but actually we do. Okay, why? Because using this number, by multiplying this number with the charge, we can actually get the amount of energy required for the charge to stay at this point, or the amount of work to be done on the charge to bring it closer just on this point, to reside at this point. Okay, this becomes our equation number 2. These are the equations of electric potential and electric potential energy. Now, for like charges, work is done in bringing this test charge closer to the other charge. and hence it's positive. So work can be positive or negative or zero. Obviously work is zero if we just don't move the charge, and work is positive if the work in the work done in bringing the test charge closer to other test charge. Okay, so for like charges the work is positive, because in case of like charges, suppose we have a positive charge over here and we have a positive charge over here. If we want to bring it closer to this charge, that work done is positive. But in the opposite case, let's take the example of a positive charge and a negative charge. Work is done in pushing this charge away from this, okay? Because in this case, the potential would be greater in this area, okay, in this area, and it would be less in this area. So potential always goes from higher potential region to the lower potential region. So we have to apply work in taking this charge away from the positive charge. Obviously and naturally this negative charge will try to just go towards this charge, but we have to provide work to this charge in order to just pull it back from the positive one. Okay, so in this case, in the case of opposite charges, the work done will be negative. Now we can take the case of electric potential. What if we have two charges? I'm gonna just change my pen. Okay. What if we have two charges? Where am I gonna draw it? We have a positive charge over here, and we have a negative charge over here. Okay, so, or we can say for simplicity, we're gonna draw another positive charge. Okay, so we have two positive charge over here. So how much work should be done to bring this positive charge from this point to this point? Of course we have to provide some kind of energy to this charge in order to bring it closer to another positive charge, because it will try to just stay away from the positive charge. These are like charges. So to bring this charge closer to this one, okay, this is the equation that we are going to use in this case. Let's suppose this is the point B and this is the point A, right? So the work done for a unit charge will be equal to, in this case, the difference between these 2 points. Okay, the difference between these 2 points. I should have wrote it over here. The difference between point A and point B. This is the charge which is producing the electric field, and as these are two like charges, they will try to repel each other. Okay, so if I want to bring this charge over here closer to the this charge, we have to provide positive work, and this work done divided by per unit charge is equal to the difference between these 2 points, the electric potential at these points. Let's suppose point B has VB potential and this point A has VA potential. Then the difference between these two potentials will give us the work required per unit charge, or simply the energy that a charge must have in order to stay at this point. This is our first equation for electric potential. In case when both the points are in electric field. But what if we have the point A at infinity? Infinity means that the point A is very far from the electric field, so that the electric field does not actually affect the point A or the charge which is present at point A. Okay, so that's why we take A approaches to infinity. This arrow is used for to determine the approaching. It means approaching. A approaches to infinity. It means that A is almost at a distance equals to infinity. Then VA becomes 0. Why VA becomes 0? As we already know that if A is so far away that it does not come into influence of this charge, so the electric field present at that point will be 0. If the electric field is 0, then the electric potential will be 0. If the electric potential will be 0, then this VA at infinity will be 0. So we're gonna just put 0 over here. So we are left with VB, which is equal to V. Of course, we are the only V have left is VB. So we're gonna just generally write B equals to, we're now gonna just generally write W instead of WAB because point A is at infinity and we don't have to write WB explicitly. So we're gonna write W divided by the amount of charge. This is the equation that is needed in the case of where we need to bring a charge from very far away from that electric field to some point inside that electric field, right? So this is our second equation, and these two equations are very important for your numericals and for your paper point of view. All right, so this is the basic equation. You can see the equation number B is the same as the equation number 1, and for if you have 2 points inside the electric field, this you're gonna use this equation. So these equations are just similar, and this is the general form of this equation. Okay, so this was all for today. Thank you so much, everyone.